Okay, the next speaker we have, guys, is Dragan Samardzija. He
Samardzija.
received his. Sorry. How do you say it?
Samardzija. Samardzija.
Samardzija. Thank you. Yeah, he received his BS in Electrical Engineering and Computer Science from the University of Novi Sad and his MS and PhD from Rutgers. He has managed research across the Nokia Bell Labs and was awarded the Bell Labs Fellow Honor. He also has authored more than 40 peer-reviewed publications and holds numerous patents. So please welcome Dragan for the next presentation.
Okay, thank you. Let me first make sure you see my material. Right, you can see it. Okay, and let me put it in the presentation mode.
Yeah.
Okay, you do see my title slide, right? You can hear me well.
Yes, we do.
Okay, I really enjoyed this summit. Very well organized, and I would like to thank Dr. Dutta in particular for leading and inviting me. And I'm here coming in front of Nokia Bell Labs. Bell Labs is a research branch of Nokia looking ahead 3, 5, 6 years. And in this particular case, I'll be talking about a few most demanding implementation-wise technologies, 6G technologies, and the associated platform challenges. And in particular, I'm coming from the platform and ASIC research lab, which I'm leading. So 6G may mean many things and may involve and will bring about many technologies. I'll be talking about the two, which in our view would be the most demanding regarding the real-time processing, the DFE, layer 1 and layer 2 processing. And I'll be introducing briefly what we call AI native 6G interface, and then the new spectrum enabled solutions towards the extreme massive MIMO. So let's describe the first one very briefly. Over the last many decades, when we think about layer 1 in particular, the modem design, it is about individual functional blocks. On the receiver side, could be pilot-based estimation, equalization, receive MIMO processing, beamforming, channel decoding, and whatnot. On the transmit side, you would do complementary things as well. However, over the last couple of years, those individual functional blocks are getting replaced by deep neural networks, or in the ultimate case of AI native radio access interface, the transmitter and then the receiver would be implemented as a deep neural network. Some of us call it deep TX, deep RX. On the top of it, when we go to the second technology, or the most demanding one, it's associated with spectrum. With new spectrum that's envisioned with 6G, we would be presented with an opportunity to introduce even larger number of antenna elements and deal with wider bandwidths. To implement extreme massive MIMO, the middle band here, which we call 6G capacity expansion layer, would be perfectly suiting such a extreme massive MIMO technology, roughly talked about between 7 and 20 gigahertz. There will be as well reuse of the existing 4G, 5G bands, and the introduction of some additional 6G bands, which I will not be talking about. At Nokia Bell Labs, we denote this middle band as the golden band for the value add reasons. Now, why is this so interesting? Why is this band of such a high interest? Within the same antenna array size, the aperture compared to 3.5, if I go up to 6, 8 gigahertz, we can pick a much larger number, effectively 4x more antenna elements. And accordingly, we can do some nice things. We can reuse the existing base station sites. We can meet through usage of multiple antennas the coverage, the same coverage we would have in the mid-band. However, the capacity would be boosted for two reasons. Number one, more bandwidth from 50, 100 megahertz. Now we can use 200, 400, 800 megahertz of bandwidth and serve users accordingly. And then as well, we are adding more antennas. And basically, Shannon-wise, we can produce higher bits per second per hertz. And overall, the cell capacity with the same cell sites, it's envisioned, it's predicted to boost the system capacity 10x, while of course being mindful of overall energy efficiency. So those two technologies I would be singling out. And this presents us with a very, very big problem. My lab is working on, and this is the compute challenge problem. Even if we do conventional processing beyond neural networks, simply through the virtue of adding more antennas and larger bandwidth, on the graph here, on the left-hand side of this figure, you see how over the years, through more bandwidth, more antennas, simply logarithmically scaled, the number of operations to perform L1, downlink and uplink processing, it's increasing tremendously. Reference point year 2000, early days of 3G. On the same graph, even though we're talking about different units, we plotted how much density in terms of gates we are achieving. We're increasing when we check the CMOS technology from early days of 2000 to the most recent 3 or even 2 nanometer CMOS technology. And we see that the needs for compute are outpacing the density of gates we can pick within a conventional CMOS. Actually, the chip to complete the link envisioned 2025 would need to be 20, 30 times bigger with all the good technology evolutions, CMOS evolution, than what we had in 2000. And this is a big challenge. And at Bell Labs, we're addressing it through different algorithm architecture and even physical chip level design. And here I'm going to show you one particular design we've been working on and became very mature. Actually, we developed a system we call compute in memory, actually a solution, integrated circuit solution, which takes us from the conventional digital processor that would be used for extreme massive MIMO or for deep neural networks, where we've got two memories for input data coefficients, be it the beamformer coefficients or deep neural network coefficients. And there'll be a lot of shuffling of data back and forth between the unit, arithmetic, logic unit, and the memory. It's a big problem known as the memory wall. And what we are doing, we have designed a system which we embed the coefficients in the memory, the blue portion of the screen. The gray boxes correspond to the coefficients, be those deep neural network or beamformer coefficients. And the data, the vector, would be coming from the left and the results getting out. But all the processing, multiply and end, it's done with an SRAM. A basic building unit of memory in digital chips. We produced a chip last year through Global Foundries, nothing fancy in terms of technology, 22 nanometers, but we showed 20x teraops per second per watt improvement over a conventional designs. And this is really pointing to one solution where we are merging extreme massive MIMO with deep neural networks and breaking one of the processing limitations associated with the problem known as the memory wall. But this is not the only thing that we do at Bell Labs. We are following these trends, call it mega trend, associated with platforms. And one in particular, it's cloud. We've been hearing about Cloud RAN, O-RAN, Cloud RAN, and this is mandatory for us to explore it as a platform problem at Bell Labs. So what do we have? We have a complete prototype proof of concept system, terminals, radio units, and then we have in the middle what I'm calling here L1 high, L2, L3, a heterogeneous pool of compute resources, CPUs, x86, ARM, GPUs primarily from NVIDIA, and Nokia Business Group, a dedicated PCI card, which carries a dedicated SoC. We call it RAN, Radio Access Network, NIC, Network Interface Card. And of course, the core functionality with it further up, typically on CPUs, and explore many things. I'll be just singling out the hottest at the moment, how we can use this heterogeneous platform to run RAN and non-RAN applications on the common cloud software and hardware platform. In particular, what if these applications are AI and whether for RAN or non-RAN. And one of the key things is, as I said, it's explorations in heterogeneous compute options. Of course, bare metal, and here I've got listed 4 of them we're considering. Bare metal would be used in classic RAN, old school, dedicated, very efficient, extremely costly in terms of engineering, R&D, and NRE. Then when it comes to flexibility, ease of programmability, total softwareization, it would be everything put on CPUs, x86 ARM, more optimized for parallel processing, but still very much in this world of software. It's based on GPUs. And there is a mix where in form of a PCI Express card, you can plug a card into a bigger cloud RAN, cloud rack, and it would be very efficiently performing typically L1 high processing rather than offloading onto the GPUs, CPUs as truly common off-the-shelf resources. At Bell Labs, we're doing all of those. I need to admit, to emphasize that currently our business group is primarily commercially offering the RAN NIC version, while for research purposes, we are considering these CPU, GPU, and the mix with RAN NIC compute resources. We are exploiting massively parallelism to achieve tens of gigabits per second, layer 1, layer 2 processing, and different layers of parallelism per user, per antenna, symbol. There is nothing new to what I'm saying here, but on this platform, heterogeneous platform, those parallelisms for 5G and then 6G need to be fully exploited. And next to the last slide, actually, we are putting together a very heterogeneous in terms of platform rack. We believe it's the future of data centers, whether far edge on-prem, but it contains a bunch of basic hosts, would be x86 or ARM hosts. There are even some RISC-V core hosts. Then the red boxes would be something we're getting from our business group, the RAN NIC card, inline acceleration. And then the most interesting part I would highlight here is this shared memory dark blue, CXL. Actually, this is a new architecture in early days of being adopted by the cloud operators, and we hope will become a reality, where this shared memory through a PCI Express and CXL switch, it's becoming a common pool between these basic hosts, very generic, common off the shelf, and these dedicated accelerators, they may be put or not into the system. And to complete this story on cloudification and heterogeneous platform for executing 5G and then 6G, this, in our view, would be in a very harmonized way can result in a system which to a large degree we have in our lab. The left end of this system, it's for common CSPs, wide area network coverage. You can see that we can have all the way down to the cell sites. We can have if I'm talking 5G language, VDU functionality up in far edge cloud as well. while on the right-hand side, I'm talking about the enterprise networks, which would rely on functionality in a far edge cloud, be it more of a public one, and then private cloud, on-prem cloud, which may have GPU resources, CPU resources for a broad set of enterprise applications, be it industrial factory applications, digital twin of a factory running and being shared with the RAN functionality. Again, 5G or 6G, Cloudify, O-RAN, it's envisioned as such. So let me conclude. When we think about 5G and then 6G, platform challenges are front and center. Simply moving to neural-based processing, adding antennas, adding bandwidth, and then dealing with heterogeneous resources, CPUs, GPUs, dedicated accelerators, and then dealing with multitude of physical deployments, on-prem, far edge, regional cloud. All of these things are presenting themselves as critical to the success of 5G, 6G, and then, of course, O-RAN as something that would be using those elements. And I would be just alerting everybody working on 6G that the 6G should not be, all the new features should not be specified in isolation from these practical challenges. I hope this is what's ahead of us, more of a holistic view through 3GPP and then the future specification of O-RAN, considering practicalities. So ultimately 6G becomes a success. I would stop here, and hopefully I did meet the reserved time. Thanks to you. Thank you.